So in the previous video, we saw how to link the line integral on the boundary of a domain of some vector fields and the double integral of the something related to that vector field inside of the domain. So very naturally, one of the applications of this is going to be to find the area of a domain. Why? Simply because you know that if you have a domain U in R2, you know that the double integral of the one function dx dy inside of this domain gives you the area of U. So what do we need? If we apply the previous theorem, I know that if I can find a vector field P and Q, so we can that such that we have that dq over dx minus dp over dy is equal to 1. I know that I will be able to relate that to then this double integral is going to be equal to the line integral of p dx plus q dy. So it's on a closed curve that represents the boundary of that domain. Okay, so let's see how we can do that. Well, of course, there are going to be many ways to define P and Q. There's an infinite number of ways to define P and Q such that this is what we have. So this is what we're looking for. dq over dx minus dp over dy is equal to 1. Then, well, let's go for the simplest one. Let's put 1 equal to 0. So if I want all the 1 to be created by this term dq over dx, I can choose q is equal to x, and then p will be equal to 0. Or I can do the contrary. If I want the whole stuff to be created by the dp over dy term, I will just need p is equal to negative y and q is equal to 0. But actually, well, a very common choice is going to be a mean of those two stuffs. So we can put p is equal to negative 1 over 2 times y, and q is equal to 1 over 2 times x. That's, I would say, is the most common choice. But you can do all well, you've got an infinite number of choices, and not only those 3 ones, but you can imagine many other ways to create the one that we have. And then what's happening? So just in here, we've written the calculations that we get. So this area is going to be given by the line integral. So in the case where you chose p is equal to negative y and q is equal to 0, this is p dx plus q dy. Okay, so the q part is just 0. In case you choose this one, so let me take another color. In case you choose p is 0 and q equal to x, you get this line integral. And if ever you choose, as we said, an average of those first two choices, this is what you obtain. And then it's just a matter of expanding that line integral if ever you have a parametric description of your curve, so that in the last choice, for instance, you will get just, if your curve is described by x of t, y of t, okay, then you've got the dx becomes so negative y, it comes the the dx becomes the x prime, so minus x prime dt, and the dy becomes the y prime dt. Okay, so these are the formulas that you get. Don't, well, of course you can learn them by heart, but you just know how to if you understand where this formula comes from, then you don't have to learn it by heart and just to redo these simple calculations each time. Okay, so so really the formula that you need to learn is that one, the Green-Riemann formula. okay, and then you just adapt it to what you need. So you remember that probably last year you studied parametric curves, and so you had parametric curves in Cartesian coordinates as the kind of the kind of curves that we've used many times, like this, the description x of t, y of t. But if ever your curve is given in polar coordinates, so in polar coordinates, I remind you that your parameter is going to be the theta, the angle, and then you define the radius as a function of the theta. So you get your given rho of theta. Well, you just adapt the previous formula, okay, the last one. 1 over 2 x y prime minus x prime y, and to the polar coordinates, so that the x of t is just going to be rho cos of t, so that the x prime is just going to be minus rho sine of t, and also you've got the y of t, which would be rho sinus of t, and the rho sinus of t for the y of t, the usual polar coordinate substitution, and the y prime is just rho cos of t. Okay, and if you rearrange that, you see that in the end it's very simple. It's just going, well, very simple. Well, it's going to depend, the calculation is going to depend on the formula you have for the rho, but then it's just 1 over 2 the integral from theta 0 to theta 1, and that's enough to describe the closed curve that's giving you your domain of the rho square. Okay, so that's it. So next we will have an example of this calculation.